What if your ESP32 could sense the weather around it? In this project, you'll build a mini station that reads temperature and humidity, processes the data, and turns raw sensor signals into useful information you can see. You've already built the core pieces of a smart system: sensing, thinking, and acting. You've used the ESP32 as a controller, driven outputs like LEDs and buzzers, and reacted to sensor input. Now we'll combine those skills to measure temperature and humidity, moving from simple reactions to useful environmental data. A mini weather station is a small, smart system that observes the air around it. Sensors detect conditions like temperature and humidity. The ESP32 reads those signals, processes them, and turns them into useful numbers. The results can then appear on a computer's serial monitor or on a small OLED screen. This flow, sense, think, display, is the foundation of many real-world data collection systems. Temperature tells us how hot or cold the air is. A value like 25 degrees Celsius usually feels like a warm room. Humidity tells us how much water vapor is in the air. Higher percentages mean more moisture, which can make the air feel sticky or warmer than it really is. Together, temperature and humidity affect comfort, weather, plant growth, and even how electronics behave. To give the ESP32 a sense of the surrounding air, we can use a DHT-style sensor. It measures temperature and humidity in one small component, then sends the readings as digital data through a signal pin. The basic connections are power, ground, and data. The DHT11 is low cost and simple, while the DHT22 is usually more accurate. Think of a DHT sensor as a translator between the physical world and your program. Inside the sensor, one element reacts to moisture in the air, and another reacts to temperature. Those changes affect electrical properties inside the part. A built-in chip measures the changes, cleans them up, and packages them as digital data. Instead of making the ESP32 interpret raw physics, the sensor sends a stream of bits. The library then turns that stream into values like degrees Celsius and percent humidity. Before wiring, disconnect USB power so nothing is live while you move jumpers. Start with power. Connect the sensor VCC to the voltage your module expects, usually 3.3 volts for ESP32 projects, unless the sensor label says 5 volts. Then connect ground to ground. That shared reference is required for the data to make sense. Finally, connect the data pin to a safe GPIO you will use in code. Double-check the sensor's pin labels because modules can arrange VCC, data, and GND differently. Then power up and test. Once the hardware is connected, the ESP32 needs instructions. The DHT library handles the timing details of talking to the sensor, so the code can stay simple. First, define which ESP32 pin the data wire uses and which DHT model is connected. In setup, start the sensor and the serial monitor. Then the loop repeatedly asks for temperature and humidity and stores each value in a variable. Printing those variables gives you an immediate test. If the numbers appear, the sensor, wiring, and code are working together. Use the serial monitor as your first checkpoint before adding a display or dashboard. It prints whatever the ESP32 sends to the computer, so you can quickly confirm that the sensor is working. Normal readings should look realistic, such as room temperature and reasonable humidity. If you see sensor not detected, NaN, or an extreme value like -127 degrees, treat it as a troubleshooting clue. Check the wiring, power, sensor pin, and code. An OLED display turns the weather station into a standalone device. Instead of sending readings only to the serial monitor, the ESP32 can write the latest temperature and humidity directly to a small screen. Most OLED modules use I2C, so the wiring stays simple: power, ground, and two signal lines called SDA and SCL. The sensor provides the measurements, the ESP32 processes them, and the display presents them in a readable format. Now the project can work without being connected to a computer. When designing a weather display, aim for instant understanding. A user should not have to decode tiny icons or guess what a number means. Use short labels, include units, and make the key readings like temperature and humidity the easiest things to see. Extra details can be smaller or left out entirely. A clean display is not just prettier, it reduces mistakes and helps people trust the information quickly. One sensor reading is useful, but it is only a snapshot. A data logger turns snapshots into a story by recording values again and again over time. If temperature is checked every few seconds or minutes, you can see whether the room is stable, warming, cooling, or changing suddenly. That pattern helps people make better decisions. It also helps smart systems act responsibly, because they are not reacting to one random value. They are using evidence collected over time. A sensor reading is not automatically the truth. It is a clue that needs checking. Loose wiring, weak power, or reading too quickly can create strange values. Placement matters too. A temperature sensor near your hand, a laptop, or direct sunlight may measure that extra heat instead of the room. Reliable systems take repeated measurements and look for consistency. If a value is missing or clearly impossible, the program should not crash or make a risky decision. It should report the problem, ignore the bad reading, or use a safe default. These same temperature and humidity readings appear in many real systems. In a smart home, they can turn on a fan, heater, or humidifier automatically. In a greenhouse, they help keep plants in a safe growing range. Museums use humidity monitoring to protect artwork and old objects. Robots can also use environmental data to decide when to slow down, avoid heat, or change tasks. In other words, sensor data becomes action. Great work! You built a complete sensing system. The sensor measures temperature and humidity. The ESP32 processes the readings, and the results appear on the serial monitor or OLED. By tracking changes over time, you also begin thinking like a data scientist. Next, we extend this idea with distance sensing, movement outputs, and smarter robot behaviors.